Ever wondered how your company's network stays totally private, even when all your data is zipping across the public internet? Well, it's all thanks to this powerful and, often invisible security architect called IPSec. Today, we're going to pull back the curtain on its blueprint and see exactly how it builds a fortress around our data, right in the middle of the open web. So let's think about the core problem here. Imagine the internet is this massive public highway system. I mean, cars are everywhere, anyone can be on it, right? So how in the world do you build a secure, private tunnel just for your data, one that's completely shielded from all that public traffic? That's the exact problem IPsec was designed to solve. To really understand how this tunnel gets built, we can't just look at the road. We've got to dig deeper. I mean, way down, to the very foundation of how the internet itself is put together. And what's so cool about IPsec is where it does its work. Layer 3, the network layer. And honestly, this is its superpower. Think about it this way. Other security, like TLS, it protects a specific app, like your web browser. But IPsec, it sits underneath everything. That means it protects all your traffic, your email, file transfers, video calls, the whole shebang, and the applications don't even know it's there. It's like this automatic, universal shield. So how does it pull this off? Well, IPsec isn't just one single thing. It's more like a team of protocols. I like to think of them as 4 architectural pillars, and each one has a very specific job to do. So let's meet the team. Okay, first up, you've got AH, the integrity guard. Its only job is to make sure data hasn't been messed with. Then there's ESP, the all-in-one protector. This one's really the star of the show, handling both tampering and secrecy. The third pillar is IGA, the negotiator, and it's responsible for setting up all the rules of engagement. And finally, you have security associations, or SAs. Think of these as the official security contracts that IK writes up. Let's zoom in on those 2 protectors for a second, AH and ESP. Now, AH is kind of the old guard. It guarantees your data isn't tampered with, which is great, but it offers zero privacy. It doesn't encrypt a thing, and it has a really critical flaw. It completely breaks when it runs into something called Network Address Translation, or NAT, and that's the tech that lets your whole office share one public IP address. ESP, on the other hand, does it all. You get encryption for privacy, plus authentication for integrity, and it's not friendly. That's why ESP is the undisputed champion that's used in pretty much all modern IPsec setups today. Now, before a single byte of your data can be protected by ESP, the 2 ends of the tunnel have to agree on the rules. They've got to authenticate each other and set up the terms of their secure contract. This whole process, it's like a secret handshake. And this brings us to IKE, our negotiator. This handshake, it happens in 2 main phases. Phase 1 has one single goal: to build a secure, encrypted channel just for the negotiation itself. So think of it like building a soundproof room before a private meeting. Then, in Phase 2, the negotiators go inside that room to hammer out the final details for protecting the actual user data. So how does Phase 1 work? It's pretty amazing, actually. First, the 2 sides agree on a set of strong crypto algorithms. Then comes the magic. Using a process called Diffie-Hellman, they can both create the exact same secret key without ever sending it across the internet. It's kind of like you both agree on a secret color by only talking about public colors that you're mixing together. It's wild. Once that key is set, they prove their identities to each other, and the result? A secure channel is up. The soundproof room is built. Okay, now safely inside that secure channel, Phase 2 begins. This is where the peers negotiate the real nitty-gritty details. Are we using ESP? What encryption algorithm are we going to use, like AES? Are we doing tunnel mode or transport mode? Once they agree on all that, they generate brand new keys specifically for this data and finalize the contracts, those 2 IPsec security associations that are going to actually protect our traffic. The handshake is complete, the contract is signed, and now for the payoff. Let's see what actually happens to a normal packet of data as it leaves your computer and gets all suited up in its new IPsec armor. So here's how that armor gets put on, step by step. An ordinary packet shows up. First, an ESP header gets slapped onto the front. Next, the entire original packet, all of your data, is encrypted, making it totally unreadable. Then an ESP trailer is added to the back. After that, a powerful integrity check is calculated over the whole thing to make sure it can't be tampered with. And for the final step, this entire armored package is wrapped up inside a brand new IP packet, hiding everything about the original. It's now ready for its journey across the public internet.
Now, IPSec can put on this armor in two different ways. First, there's transport mode. This is where it only encrypts the data itself, perfect for securing traffic between two specific computers. But then there's tunnel mode, and in this mode, it encrypts the entire original IP packet, headers and all, and wraps it in a new one. This completely hides where the traffic is really coming from. And that right there is the magic behind almost every single VPN you've ever used.
So IPsec is incredibly powerful, but it's not perfect. Like any really complex piece of engineering, it has some incredible strengths and some notable challenges. Let's take a look at the final scorecard. On the plus side, its security is absolutely comprehensive. It's totally transparent to your apps, and it uses really robust modern cryptography. It's incredibly flexible. But on the other hand, all that flexibility leads to some serious operational complexity. I mean, it can be a real beast to configure and troubleshoot. It also adds processing overhead, and its relationship with NAT, while definitely manageable with ESP, can still be pretty tricky. So, to sum it all up, this is the IPsec blueprint. The core equation is actually pretty simple. It's the combination of its protection protocols, its negotiation protocol, and the security contracts they create. It's got two modes, transport for hosts, tunnel for networks. It uses that two-phase secret handshake to establish trust, and its final verdict is a balance. It's immensely powerful and universal, but it's also pretty demanding in its complexity. At the end of the day, IPsec is the invisible shield protecting a huge portion of the world's private data. Its architecture is complex, for sure, but it's really a masterclass in security design. So the next time you connect to your VPN, maybe you'll picture that secret handshake and those armored packets just working silently in the background to keep your data safe. And now, you know how it's done.